When you open a food delivery app, the interface feels effortlessly simple. You scroll through restaurants, pick a meal, and hit order. But beneath that clean glass surface is a battleground of competing data streams. Look at the traffic generated by millions of simultaneous users. If you force this data through a single monolithic pipeline, the pressure destroys the system. This graph maps out the different traffic profiles tearing at the infrastructure. On the left, we have search queries. When users are hungry, they browse endlessly, creating massive, sudden waves of read requests just to load menus and images. Next to that is a very different kind of load. These are the transactional payments and order placements. The volume is much lower than search, but the requests are critical, requiring rigid, lockstep processing. Finally, look at the far right. This dense, erratic jitter represents location updates. Thousands of delivery drivers are constantly pinging their GPS coordinates back to the server, creating a high-frequency barrage of write requests. If you route these three radically different read and write profiles, massive searches, rigid transactions, and relentless GPS pings into a single database, you create a fatal bottleneck. The database locks up trying to write driver coordinates while simultaneously trying to serve millions of menu reads. To survive this volume, the architecture must be decoupled. The system has to be broken down into independent microservices, engineering each specific component to handle its unique traffic behavior. Let's isolate the search traffic. When a user searches for a restaurant, human psychology dictates a strict non-functional requirement. The system must return results in under 400 milliseconds, or the user closes the app. This diagram shows the initial routing. Incoming search traffic, represented by these blue particles, hits a load balancer and is instantly directed to a dedicated search microservice. But watch what happens if this search service queries the primary NoSQL database directly for every single request. The flow throttles to a crawl. The mechanical failure here is database I/O limitation. Scanning a massive primary database to match text strings and filter complex restaurant attributes consumes too much disk read time, pushing the response well past our 400 millisecond limit. We solve this by inserting a high-speed query layer. We pull the primary database out of the direct traffic flow and place an Elasticsearch node right in the middle. Now, the requests route through Elasticsearch and return to the user instantly. Elasticsearch absorbs this heavy read load because it doesn't store data like a traditional database. It indexes the restaurant and menu data specifically for rapid, text-based retrieval, operating largely in memory. Separating the search index from the primary source of truth creates a trade-off. If a restaurant updates its menu or suddenly closes in the primary database, the search index won't know immediately. The search might show a closed restaurant as open. This introduces the concept of eventual consistency. The system deliberately accepts temporary data staleness in exchange for maintaining sub-400 millisecond query speeds. To mitigate the staleness, the engineering team establishes a service-level agreement. This SLA defines the exact cadence, perhaps every few minutes, that the primary database recomputes and syncs its latest state with the Elasticsearch index. For read-heavy discovery features, prioritizing extreme latency over absolute real-time data freshness is the necessary compromise to handle millions of simultaneous users. Once the user finds their food and clicks checkout, the rules reverse. Financial transactions cannot tolerate eventual consistency. They require absolute, immediate accuracy, even if it takes longer to process. The load balancer identifies this intent and routes the checkout request, our green traffic here, to an entirely independent order service. Because payments demand certainty, the communication here is synchronous. The order service pings the payment service, locking the two nodes together in a rigid chain. The payment service then initiates an external API call to a third-party processor, like Stripe. This creates synchronous blocking. The entire chain must wait, holding its state in memory until Stripe returns a definitive success or failure message. No further action can be taken until that answer arrives. Once Stripe confirms the charge, the success signal travels back down the chain, triggering a final write to a designated order SQL database. This specific node uses a traditional SQL database because it leverages ACID properties: atomicity, consistency, isolation, and durability. This mathematical strictness guarantees that financial records are never corrupted or only partially written. But this synchronous loop carries a severe risk. If a user's network connection drops while waiting for the confirmation, their app might retry the exact same payment request, creating the potential to charge their card twice. To prevent this, the architecture relies on an item potency key. Before the payment request ever leaves the user's phone, the client application generates a unique cryptographic hash string and attaches it to the data packet. When the payment service receives the request, it checks this key against a store of recent transactions. If it sees the same item potency key twice, it safely rejects the duplicate packet, ensuring the user is only charged once. This pathway is slower and demands heavier resources. But by isolating it, we guarantee financial integrity without choking the speed of the search layer. With the order placed, the engineering focus shifts from the consumer to the physical delivery network. The system now has to track thousands of moving vehicles in real time. This requires managing the sheer volume of thousands of active driver apps, with every single driver pinging their GPS coordinates simultaneously, second after second. This creates a deeply asymmetric traffic profile. It is hyper-frequent, aggressively write-heavy, and completely asynchronous. Look at what happens when this massive wave of location updates blasts into a single driver location data store. Writing the location of every driver across an entire country into a single table creates immediate table contention. The database spends all its compute power locking rows to update coordinates, crashing the node. We resolve this write contention through geosharding. The architecture splits the single NoSQL database into multiple independent databases, defined by strict geographic boundaries. The logic is straightforward. A delivery service routing an order in Seattle has zero need to query the location of drivers in New York. By physically dividing the data by city, we drastically shrink the search space for the matching algorithms and entirely eliminate national write contention. We optimize further by reducing the sheer volume of traffic before it even reaches the load balancer. Rather than having the driver's phone blindly ping the server every single second, we implement a client-side filtering mechanism. The application calculates delta shifts locally on the device. The app applies threshold logic. It only executes a write request over the network when the driver moves a significant, measurable distance from their last recorded coordinate. This silently eliminates millions of redundant pings. Finally, to handle assignments, we use a rapidly accessible state store. This specifically maps one driver to exactly one active order at a time, instantly checking a driver's availability and preventing double assignments. Surviving high-frequency write traffic requires attacking the problem from both ends, partitioning the database geographically on the backend and aggressively filtering the noise locally on the edge device. This diagram illustrates the completed microservice architecture. A load balancer sits at the top, splitting incoming traffic into 3 distinct environments. On the left, the read-heavy discovery path relies on Elasticsearch and eventual consistency to prioritize lightning-fast query returns. In the middle is the synchronous transactional path. It utilizes SQL, strict ACID properties, and item potency keys to guarantee flawless financial exchanges. And on the right is the asynchronous, write-heavy path, dependent on geo-sharded NoSQL and client-side delta filtering to track real-time logistics. Scaling a system isn't solved by simply plugging in more servers. It is achieved by matching the correct consistency model and database type to the specific behavior of the data. The ultimate benefit of this decoupled design is fault isolation. If a sudden spike in traffic crashes the Seattle driver database, users can still search menus and place orders without the entire application going offline. In modern distributed systems, architecture is an exercise in isolating bottlenecks. It ensures that competing data profiles can flow at their own required speeds without destroying each other in the process.